In this video, we're going to do a second example of an integral which has a discontinuous integrand. Notice that in this particular case, it's not at all obvious that there's anything suspicious going on. We have nice finite limits of integration, and if we naively thought through what we usually do, which is this is an integral from 0 to 4, I have some function, I'm going to have a graph, I'm going to find the area underneath it, that would be great. Except in this case here, lurking beneath the surface, is a problem with the denominator. If we factor that denominator, we can get x plus 3, x minus 2. And then we notice that the graph that we see for this function would not look like this. If you look carefully at this x minus 2 term, when x equals 2, we're going to get a division by 0 problem. And so what that's going to lead to is some kind of asymptote around the point x equals 2. And then we're into our territory from the previous example where we don't know in advance whether there's going to be a finite area under this graph or not. We're going to need to use our limit technology to evaluate that. So how do we do that? We're going to break it up into two intervals. And then we're going to evaluate each one separately. So we have two intervals, 0 to 2, 1 over x plus 3, x minus 2, and then add a little bit of color here. We had 0 to 4, now we're going 0 to 2, 0 to 2, and then 2 to 4 to be able to cover the original interval. Same integrand, and we just put our 2 down here at the bottom. So again, as long as we start at 0, get to 2 and pause, and then keep going from 2 to 4, we're fine. It's the same integral, but now each of these is a singly improper integral because the only point that's an issue here is the point x equals 2. At x equals 2, our integrand becomes undefined, and so we have to sneak up on it with a limit. Also, this one is also a singly improper integrand because the 2 again is a problem, but now we're going from 2 to 4. So let's give these some names and call them I1 and I2. And if we just focus in on, say, I1. If we look at I1, we have the integral from 0 to 2, but we're going to use our definition for improper integrals. And that definition is going to say we can't go to 2. Instead, we can go to some upper limit, let's call it b, and later on, we'll sneak up on that 2 value by letting b approach 2. And if we're talking about intervals here, we're going to creep up on that from the left as this lower boundary moves closer and closer to 2. And the integrand doesn't change. So this mechanism here again just reminds us that if we integrate from 0 to some number, that'll be a nice finite area. We can calculate that area depending on b, and then we ask, well, what happens if b got closer and closer to 2? What would that area overall tend towards? Either a number, finite and convergent, or something infinitely large, divergent integral. All right, next up, we have to evaluate this integral. This is a classic example of an integration by partial fractions, so we're going to do that on the next page. So we have partial fractions, and our 1 over x plus 3, x minus 2 is going to equal some number a over x plus 3 plus some number b over x minus 2. And then we do our classic common denominator calculation. That term is missing the x minus 2's. That term is missing the x plus 3's. And when we multiply that out, we're going to get 1 equals ax minus 2 plus b x plus 3. Nice distinct linear factors. And then we can do our little shortcut where we let x equal some number. For instance, if we let x equals 2 here, we're going to get 1 equals 0 times a plus b times 2 plus 3. b equals 1/5. And if we do the same thing again, but this time letting x equal -3, we have this equation transformed. The left-hand side still 1. The right-hand side is now a times -3 minus 2. And then the b is times 0, so we don't have it. And so we end up with a equals -1/5. So our first integral, I1, which was, going back a page for a moment, the integral on the left-hand side here, the area under the graph, which is the integral from 0 to 2 of this expression. We recognize that it's an improper integral, so we have to handle it with care. We do that here with the limits. So it's the limit as b goes to 2 from the left, of 0 to b, of this thing here, and now we have a decomposition of what's inside. So we have our limit, b is going to 2, our integral is from 0 to b, and now we have our a is -1/5, and a went with the 1 over x plus 3, and b was +1/5, and it was over x minus 2. Brackets. And now we can integrate. When we do that, we get, again, the limit as b approaches 2 from the left. Here we're going to get -1/5 ln of the absolute value of x plus 3, and then +1/5 ln of the absolute value of x minus 2 between b and 0. Just clean up that negative sign a little bit. Then we sub in b and 0. We're going to get the limit as b approaches 2 from the left of -1/5. Then b is the upper value, it goes in first. Ln of b plus 3, 1/5 ln of b minus 2. All of that minus the same thing when we sub in 0, -1/5, 0 plus 3 is just ln of 3, and +1/5 ln of minus 2. Oh, that would be a problem, except we do have absolute values. So absolute value of -2 is totally fine. Again, just cleaning up some notation here. So this is the area underneath the graph from x equals 0 to x equals some point b that we don't know yet. But as we push b closer and closer to 2, as b goes towards 2, this goes towards 5. 2 plus 3 is 5, that's fine. But this one heads towards 0, and ln of 0 is undefined. That actually heads towards -infinity. So as we look at all the terms and we try to evaluate this limit as b approaches -2, we actually have an improper integral that diverges. So we're going to go back to our original statement here. This part of the integral diverges, and it doesn't matter what the other one does. The whole integral from 0 to 4 of what we started with, x squared plus x minus 6 dx, also diverges. As soon as one piece of the puzzle diverges, then the whole entire integral also diverges. So this is a lovely combination of recognizing an improper integral when it wasn't obvious, but noting as we do our factoring to do the integral, it makes it a little more clear that there's a problem if we look at our interval and where the denominator gets undefined, or rather, where the denominator equals 0. And then as we proceed with our calculations, it's exactly like the earlier examples where we use a limit, but the limit's the last thing we do. Most of our attention is simply on evaluating the integral until we get that done, and then we imagine what happens as we push here b towards 2, and recognizing when those limits become undefined, meaning that the overall integral diverges.